So before jumping into implementing all those helper functions, I thought I'd take a step back and have a look back at over the kind of algorithm W and figure out what are the helper functions we actually need here. So in this case, remember this is algorithm W. We very quickly skimmed it in the kind of last video, but we've got this thing here, right, where we say, well, for all alpha tau, that's kind of this thing. This is what we're getting X out of the context for. But we now need to instantiate it. So we've got this new vector beta of all these new type variables. And so these are all going to be new type variables. So we need a function to create new type variables. And basically we're going to substitute all of them in. And so that kind of repeated substitution across all these different variables, and also identifying which of the variables we need to kind of create a new, this finding out this alpha first and then replacing them all with new ones beta. We're going to have instantiate and kind of new type variable functions for that. And then here you can see there's like lots of other news. So we're going to have like that new type variable function. What else do we have? Well, here, for example, we are applying this substitution over this type. And so we need to be able to apply substitutions. So remember we had substitutions, we need to apply them. And we've also got stuff here like this where we have, multiple substitutions. So we want to kind of combine these substitutions together. So we need a substitution combining function. And remember, we've looked at all these things before in previous videos. You can go and check them out if you haven't seen them before. So I combine them. And then also, where's the step I'm looking for? This U symbol here, this weird squiggly U is the unify function where we want to say, well, these two types, so this little comma separates these types. So substitution 2 applied to tau1 is some type, and tau2 to B is some other type. These two types should unify, and we want to find a unifying substitution. So the substitution that makes both of these the same, and that's going to be substitution 3. We need to implement this unify function. We've already seen it implemented in TypeScript. We just need to do that again. And then also other things we've got here are this kind of, we call it clos here, but this is also known as like the generalize function. So we need to generalize as well. And so skimming through the slides again backwards, we had this instantiation thing, right, where we're saying, well, we can substitute all these different things in an instantiate type. We can generalize the thing, so that's like the clos thing. We can combine substitutions. So that's where we have, if we combine substitution 1 and substitution 2, we should get a kind of equivalent substitution. The kind of return value of this should be the same as applying S2 and then S1 to kind of anything. We also found unifying substitutions. So that's where we want to find a substitution S such that it unifies two expressions A and B. So that when we apply S on A and S on B, these two result in the same thing. And then also we want to look at the unification. So this is kind of a imperative written. It's not quite TypeScript, but it's not too far off written way of unifying things. So how we can implement that and how we can actually find those substitutions. So let's jump back to the TypeScript. So back here, I've got down what we were just talking about. So we've got substitutions, so we want to apply and combine them. We want to create new type variables. We want to instantiate some types. We want to generalize some types. And we also want to unify some types to get unifying substitutions. I'm going to actually take all these topics and pop them in a kind of new helpers file. We can maybe split this file up more later, but I think that's sufficient for now. And so for substitutions, there's kind of the simple, naive way of implementing them. And like this is also perfectly fine. But you could say a substitution is going to be some kind of map, right? So it's a map from type variables, which are going to be strings. And it's going to map them to monotypes, right? And that's effectively what a substitution is, right? Where we could say, well, we're going to map a variable to a monotype. What we're going to do is we're going to do something a bit clever here, and we're going to actually be able to use simpler syntax. So for example, if we were using this syntax, what we might have to do is something like apply S1 onto some type T1, which is not too bad, but it makes it look more different to the algorithm than if we could just do like S1 on T1. And this is a bit shorter and it's a bit closer to how you'll see it in kind of the literature. So that's quite useful. And TypeScript actually allows us to do this. So rather than a substitution being just a mapping, what it's actually going to be is we're going to define it as a function that you can then apply to two kind of types. So we can say, we're going to keep that for a second. We can say a type is going to be a substitution if it takes a type, which could be a polytype, and then returns a polytype after it's been applied, right? So something like that might work. We'd also need to kind of expand this so it can also support monotypes, etc. And we also want to apply them occasionally on contexts, I think. So lots of different things that we might want to get working there. Additionally, occasionally it might be useful to like take out these kind of different type variables as the raw values so we can combine them together. So what I'm going to do here is actually kind of have this kind of overloaded function as well as have properties on this function that we can pull out the raw things. So I'll give it a type name of substitution. This I'm just doing so, if we do later have to debug, we can like always just do .type on lots of things and it will tell us what we're actually dealing with. So our polytypes, that looks good. Just because TypeScript is weird, you have to change the syntax slightly, but this basically means the same thing, where if we have a substitution, so we can say S is going to be a substitution. We could then call S on a polytype and we get a polytype back, so that's fine. And other things we want to do is we might want a monotype version of this. So actually, if you substitute something on a monotype, because it's just a map to monotypes, it'll also stay a monotype, and that's cool. And then similarly on context, we want to apply the same kind of logic. And then lastly, as I said, we might want to maintain the kind of raw underlying substitution so that we can combine them so that we can actually apply them and figure these things out more easily. So I'll save that as a, what would we say? I think, oh, actually we had it here, right? So we can copy this one. Which is like under the hood, this is really how they're working. So what I'm going to do is write a function that can create a substitution. So we'll say make substitution, and this is going to take our kind of raw thing here. Actually, I could probably do substitution raw. There we go. So it's going to take our raw kind of definition, and then it's going to return us a substitution that kind of implements that. And so when we say return a substitution, what we mean is return something that has this type, which has, it's a function that can do all these, it's a polymorphic function that does all these things, as well as it has this raw property. So what's that going to look like? Well, we're going to have a function. And so the arguments it needs to take are probably going to be this kind of typey thing. I'm just going to say that's an argument. And that's either going to be a monotype, or it's going to be a polytype, or it's going to be a context for now. And what it's actually going to return as well is going to be a monotype. Or maybe we can leave it out and TypeScript will infer it. And if it doesn't, we'll add it explicitly. And actually, this function is going to be pretty simple. It's just going to apply that function to whatever we've got. So we're going to apply this substitution onto the argument. And we'll write that apply function down here in a second. So what I'm going to do next is apply the kind of properties. So we've got type and raw. So type is going to be substitution. And then raw is going to be whatever we passed in as raw. So that looks good. Yeah, that's fine. We just need to return it at the end. Is it going to be happy with that? Okay, it's very confused. So I think we could do as substitution here. I need to wrap this in brackets. There we go. Cool. That looks good. And so now we can do make substitution and then say, x should be a type variable. Or actually, x should be type variable. And then, the value should be whatever, right? And what that would mean is wherever we see this type variable x, it'll map it to whatever this type variable is, which is like AJL SDF or something. So that works. We actually need to implement this apply function. And the other thing we might want to do is similarly, if we had like S1, S2 on something, or like just S1 applied to S2, like we have in algorithm W at some point, we just combine three of them. Maybe if this is being applied onto a other substitution, we might want to combine them, but we'll deal with that as well when we come to it. So let's define an apply function. In this case, I'm going to use function keyword just because then we can have the polymorphic type work a bit easier. So if we have some type monotype or polytype or polytype or context, and then we have our substitution, right? This is what our substitution we're passing in is going to be as that, and then the value we're applying it to onto it. So I don't know what to call this, but I don't know. Value is going to be t. Then we're going to return a t. And so what this is useful for doing is saying that if we're passing in a monotype, we're going to get a monotype back. If we're passing in a polytype, we're going to get very similar to this, except it's just a short way to define it for our apply function, and then we actually have to implement it. So our substitution, and then our type is going to be r. And the reason we're kind of giving it these two definitions is because TypeScript is not quite clever enough to realize we're not changing the type of it over this thing. And so, yeah, this one basically tells it, no, we're keeping the type, and this one tells it, look, for your purposes, you just need to check that it's doing it's turning one of these into one of these, which it's definitely going to do, and it's going to be happy confirming that. So first thing we should probably deal with is contexts, because monotypes and polytypes are pretty similar. We should get context out of the way. So if something is a context, so I can't remember, how do we represent contexts? Okay, we had a map from variables and polytypes and other things. Or polytypes and monotypes always had some form of like type on them. I wonder if we could use that. I guess it's like a bit weird if we have a variable called type. That could cause problems. But we could also add a symbol in here. So we could say a context always has a particular symbol, and then we can have a make context thing. I might do that actually. So we'll have context marker. It's going to be new symbol. And then here we'll have a context marker, and that'll be mapped to. It doesn't really matter what it's mapped to. Just map it to Boolean or something. And then we can have a make context function, which could take our raw thing, which is going to be this. That looks good. And now it's just going to return our. To be honest, we can just edit this existing thing, right? We can just do raw dot text marker is true. This is going to be unhappy because yes, okay. If we tell this thing is actually this with that optional, let's see if that does what I'm expecting. Well, we have some variables, so we can say x is a polytype, so that will have to be like type is. Okay, great. Okay, and now we have a context, and so we should be able to say C is context, and then C context marker. Okay, good. And export that, and then here I might have a little helper function, which is like export const is context, which is given a something which is unknown, and it's going to return whether something is a context. And all this is going to do is say if the type of something is an object and something indexed by context marker is true. It just needs to return that, I think. Something is possible. Oh yeah, and something is not null. Okay, that should work for us now. And so here we can say, so if the value, if the value is a context, I just need to import that. Then we need to go apply it to everything in the context. So what we do is basically just map the object. We use some of the helper functions with that. So we do object from entries, and get the entries from our value, and then map each of these key value pairs to the same key, because we don't want to change that, but we want the value to be, we want to apply it to the value, I think. So the same substitution applied to the value. Why is that unhappy? It's not assignable to, because it is not a context now. Okay, so I'm happy about the return type. I'm slightly worried that when it gets the entries, it's going to get that symbol entry. I guess we could filter out that symbol entry. So filter such that if we take the keys, is that going to work? The key is not going to be the context marker. I don't quite know how symbols interact with this kind of stuff. I should really split this up, sorry. So we take the entries, filter, map. There we go. And then we're going to make a context out of that to add back that entry. I think that should work. Why is this still unhappy? Oh, because you never told it that this should be a context. So that should be returning a context now. Okay, that's all happy. Oh, I should quickly test how this works. I'll be back in a second. I'm going to test out that. Okay, I'm back from testing that, and apparently it just kind of ignores the symbols, so I can remove that. which should be fine. Next, we're doing monotypes and polytypes. So, I mean, basically we can lump these all in 3 cases, right? Which is, it's either a, what was it over here? It's either a type quantifier, type variable, or type function application, because monotype is just kind of one of those 2. So it's going to have one of these 3 values. And I think actually TypeScript should already know this for us. So if we do something like if value.type, there we go. So we've got the 3 different kind of cases. So easiest one is a type variable. What we're going to do is, so now it should know that it's type variable, so it has this a value, and if that is in the substitution, then we need to map it. So if what is it called? Substitution raw. I'm just going to rename this to S to make it shorter and easier to deal with. So substitution raw has this value a in it. Then that's what we basically want to like map this to. So we're going to map our type variable to a monotype. And so if we have that substitution there, we can like return whatever the value is there, because it should just be mapped to that thing. Otherwise, we are just going to return the type without mapping it, because like it doesn't need any changing. What are the other cases? So if this one is a type application, in this case, remember this is the kind of C and then like a load of different monotypes. What we can do is we'll always say the type function like the type function is going to change, but it's only going to be all the arguments, so we're just going to have to map all of those through. So we could return, I guess, the same value, I think, except the muse should be the muse all having been mapped such that the arguments is, I think we want to just apply the same substitution on all the arguments like that. Sorry, I called it S now, didn't I? And then for type quantifiers, again, not much is changing, but we need to map the kind of inner bit, so we can probably just copy this really and say that the only thing that is changing is the inner bit, which, what should we call that? We go back to this one, we call it the sigma polytype. So sigma is going to be the same sigma, except we're going to apply the substitution to that thing. So you can see again, we're kind of creating this quite recursive algorithm. Why isn't, oh, this should be value.sigma. Is still angry at us? I guess it doesn't know for sure at the end what's going on. So value, what is it? Okay, value it thinks never. So it should never get here, but it doesn't know that. So we could just throw like a new error. Unknown argument passed to substitution or something like that. It should never really get there, but just in case. So again, now we can test out these substitutions. Let's give that a go. So we'll say our substitution, we're going to make a substitution. It's pretty simple, and it just changes the type variable A to the type variable B. I guess just not to confuse ourselves, I'm going to call this X. It's gonna map X to Y. So this is kind of equivalent to, I think in our presentation we had some kind of format that looked a bit like that, right? It's gonna map type variable X to Y. So let's give that a go. So let's say we had S and applied to a monotype, which is going to have the type variable X. What we should expect is that it should map to Y. So if we bring up the console again, it is crashing, which is not good. Okay, let's have a look at that. Okay, so I think it doesn't know what this thing is, and so it's not certain that it can like look up context marker on top of it. We say context marker in something. Let's try that and see if that is gonna work for us. Okay, it seems happy. We'll have to double check that one actually works, but I think it should. Let's see what our substitution does for us. So we can see, yeah, when we pass in a substitution and we have a type variable that is just an X, it then gets mapped through our substitution to Y. So again, if this was like a Z, it wouldn't get changed because that doesn't match our kind of thing here. So the Z stays, but when it's an X, it gets updated to a Y. And similarly, if this was like a more complex type, so imagine if this was a type let's say it's type function application, and the type function that we were dealing with is, say, the function type function, and then the arguments are going to look something maybe like the first one is going to be another type function application. In this case, it's just going to be bool, and there are no arguments for this one. And then this one is going to be a type variable, and it's going to be x or something, right? So this is the equivalent to the type. So it's a type function application from bool to x. And what we should do is after we apply the substitution which takes x to y, it should result in bool to y. And we can see that's exactly what we get, right? We get a type function application, which is of the function type function application from bool to y. And similarly, we could swap this out for kind of different things, but that's basically what it could do. So again, here actually, if we wanted to swap this out for x is going to turn into a bool, which is going to be a type application, right? We could do that, and then we can see that's updated where we had this type variable, which was x, it's updated there. And so this is going to be really useful for applying our substitutions, especially after we unify stuff and then we want to make them the same. We can do that like that. Okay, great. So that all seems to work. Our applying substitutions seems to work. What we need to do next is combining substitutions, and then we should be pretty done with our substitutions. So let's have a look at combining. I'm going to hide the terminal again, get us a bit more space. You know what? Let's do this kind of defining substitutions altogether, applying and combining. And so I'm going to say, let's say you had this syntax where you have S1, S2, S3. I'm going to say that means like really these three substitutions should be combined. And so what we could take here as an argument, we could say, well, if you're passing a substitution to a substitution, then we should pass that as like combining. So if, so here this should actually also accept a substitution. If the arg type is a substitution, then we want to combine this function and that argument. So that's going to be the two substitutions. Yeah, we'll have to make sure that we're doing it the right way around, because that can be like a little tricky, making sure the substitutions are combining in the right order. But I think this should be right. And yeah, remember this dot type thing is coming from where we define the type up here. So let's write our combine function. So I'll go down here, and we can write our combine function. So combine should take a substitution, two substitutions, right? S1 and S2. And it's going to return their combined substitution. And if we remember what combining substitutions means, really that means it should be equivalent to applying S2 and then S1. And then combining them, that combined substitution should be equivalent to doing them in that order, because it should look like S1, S2, and then the target, right? Or type or something here. So the combined substitution should be like S1, S2. That should be kind of equivalent. And so we want to make sure that S2 is applied entirely, and then S1 is. And you kind of imagine it going backwards. Well, if like T, if S1 was something like X goes to Y, and then S2 was something like Z goes to X, and T was Z, what it's going to do is it should take Z, take that to X, and then X take that to Y. So it's like passing them through backwards, right? And so we can implement this is basically just combining these two objects and making sure that wherever S2 has something that then maps into something in S1, then the final result should be kind of this last object. So let's give it a go at implementing that. So what we're going to do is we're going to return kind of a new substitution that's going to be the combined object of the two of these. And so that should be everything in S1, right? Because if it was in S1, that's going to be applied afterwards. And so like all the rules from S1 should just be applied straight off. There's no further transformation. So we're going to do s1.raw, right? And raw was going to be our kind of, our mapping here, which is what we want to pass into our new make substitution. And the other thing is we want to take everything in S2, except where it's like kind of done this special case where the result of mapping it through S2 is then mapped again in S1. So it's almost like we have to apply S1 onto all the kind of 2's in the S2 side. And so let's look at that. Well, we use the same trick where we did this kind of object mapping, where we're going to do object from entries, and then we're going to do object entries, and get everything in S2. and then map that through so that anything which kind of matches here gets mapped through. And the way we can do that, where this might be more complex, right? We can't just look at the variable name. So this could be, say, bool to x, right? And then suddenly that's got a lot more complicated in like how we might, those are just make clearer, a lot more complicated in how we can map these. What we can do is just apply this substitution on this result, and that will map this again to bool to y, and then we've done basically what we want to do. And so we're going to take our key value pairs. Remember, the key's not changing. The z is staying the same, but the value we can apply our substitution s1 to, well, really we can just do s1 applied onto this value here. So something like that. And why is this a little angry? Oh, because we still need to keep the key. There we go. So we're going to map it to like having the same key, and then applying that first substitution on top of that. So that should combine our substitutions. We can actually test it out on this case if we want. So we can probably delete all that. So S1 is going to be, we're going to make a new substitution, which is going to map X just to the type var Y. And then S2 is going to be a substitution where we're going to take Z and it should be a type application with the type function application of the arrow, and then the, what do we call the R's? The muse should be, well, the first one is going to be a bool, so that's going to be a, let me copy that, a type application of type bool with no arguments, and then the second one will be our type variable x, right? So our is x. Great. And then if we have log s1, s2, what we should hopefully see is, I think, did we write it down here? Oh, I can't remember if we wrote it down here. But we should have z maps, through the x to y. So it should be x still goes to y. That's the case there. And then z goes from, well, it's a mystery because we've got this problem again. Let's do this. Okay. Z, there we go. So Z is now is mapped to a type application from bool to y. And so that's done kind of exactly what we expect when we want to combine them. So that's all looking good. So I'm going to hide the console, get us a bit more space, and have a look at what next we've got. We've got creating new type variables, we've got instantiating and generalizing types, which are going to use our new type variables, I think. And then we've also got unifying types. So let's jump into creating new type variables. So this is going to be pretty simple. I'm sure there's maybe a nicer way you could do this. I'm going to do it quite simply. I'm just going to create a kind of global variable that's going to keep track of where we are. I mean, you could put this in a weird closure, or you could do something strange here. But yeah, keep it simple. So I'm going to say, let current type var 0. And then whenever we want a new one, we're just going to increment that and kind of create that. So when we want something like, I don't know what to call this. We'll just get new type var. Again, keep it simple. We're going to say this is going to return a type variable, which in this case is going to look something like type is type var. Why is this unhappy? I feel like it's imported type variable from a different, it's imported it from the TypeScript internals rather than my models. So let's go back there. Maybe I should name these slightly differently to avoid that. There we go. So we have a type var, and then a name is just going to be, let's say, t, and then the current type var that we're going to increment. So what this is going to do is the first time we call it, so again, we can have a look in here. Import that over and create a load of them. We can see, the first time it's going to be t0, then t1, t2, etc., and kind of go down like that, which is exactly what we want. Each time it's going to be a new one, and I mean, there's potential for a clash if you did have a type variable named that, but it seems very, very unlikely that you'd have a type variable named that it's going to clash, because they'll all be generated basically by this method, so it'll be pretty safe. Okay, so next function is instantiate. So create a function called instantiate. And what it's going to do is it's going to take a type, which is initially going to be a polytype, and it's going to instantiate it with new type variables such that it is a monotype. And so remember, this was looked like, say, for example, for all A, for all B, you know, A to B. I don't think this is even a valid type, but let's say it was that. Well, then maybe you could instantiate it as, you know, interval or something like this, right? Or really instantiating it here, we just mean instantiate with new type variables. So it would be like T0 to T1, right? Without these for all quantifiers. So it'd just be that. And we can, you know, again, change these things. So instantiate, we're replacing all the for all quantified variables with our new type variables. So in this case, again, we can look at the type. Probably be quite similar to, I'm going to hide the console again, get us a bit more space. Probably be quite similar to this, where depending on the different type that we're being passed in, we're going to do different things. So initially, if the, I think we're calling a value here, but well, type. It's a bit strange that we're calling it type, but that's okay. Well, if it is a type variable, well, then we need to see if it's something that we've already kind of mapped or changed. And if so, get that mapping. So for example, if we did have that case, which was for all A, for all B, A to B, right? At the time, we would have like, when we processed this polytype, we would have converted this like A and say, okay, well, we're going to remember, like we have some mappings that are going to look like, well, A should go to, it's almost like a substitution really. A is going to go to T0, right? And then later when we get to this A, we're going to replace it with a T0. And then we get it like T1, and B would go to T1. So we'd have something like this. We have a T1. And so for our type variable, that's what we want to do. I'm going to go in and say, well, the thing we want to return is our mappings. Either get the kind of the type for that thing. So if it's an A, we should map it and get this T0. Otherwise, if it's not there, then we're just going to return the same type, because we know it's a type variable, which is monotype, which is fine, and it's not in our mappings. We need to actually record these mappings, and so at the beginning we don't have any mappings, but we want to kind of gather them over time. What we could do is have like an instantiation function that just calls like another function that we call like, I don't know, underscore instantiate, which passes in an empty map to start it off with. I'm going to do that kind of starting off with by just, you know, passing it in as an optional argument that kind of, so it can recursively call itself with this mappings when it needs to go down. So this should be a map from, I guess, string to type variable, something like that. And initially it should just start as an empty map. So I'll put these on different lines maybe, and that would make the formatting a bit cleaner, something like that. Great. So that works. This is still complaining. I guess we have to also copy our little throw statement here. So we've got like an unknown type passed to instantiate. Good. So if it is a type function application, in this case, there's, again, very similar to this one. There's no real work to do, right? So if we had this like A to B, it's still going to be whatever this thing is to this thing is. We just need to pass it down so all these other like things are mapped in here. And so we're just going to have the same type, except the muse are going to be mapped around with instantiate again. And we're going to pass in the mappings that we're keeping. And what are we going to pass in here? I think we just want M. Yeah, that looks right. Cool. And then if it's a quantifier, that's when we have to generate this new type and then add it to our mappings like this. So we have to look at kind of what the value was and add that. So here we can say mappings.set. And the thing we want to set is going to be our type.a, right? Which is going to be our whatever this value is. So that's the kind of key. And the value we want to map it to is a new type variable. So we can call our nice new type variable function over there. That looks good. And then we can just return instantiate whatever the kind of child of this is. Like this kind of just like gets deleted and we just add the mapping and then, you know, continue on. And so the sigma was kind of the like next level down. And that's good for our instantiate function. Again, we can test that out. So if we had instantiate on, let's say we had a, I don't know, I guess we need a quantifier first. So we could have a quantifier and it's going to be, let's say kind of name of it is maybe Z. And then the actual kind of child of that is going to be, say, a type variable, which is just going to be Z as well. Let's say this is type variable. And then the, what do we call the name again, is Z. what this is like looking like is for all z. Well, then what we should get is when we instantiate this is we should get like t0, which could be any type, right? Because this z is going to get deleted, and then we're going to add to the mappings that z should go to t0, and then it's going to map to t0, something like that. So again, let's have a look at that. So if we log this, log the console. Oh, we've got a crash. Do we not export it? Do we not just hit? I just didn't hit save. Okay, there we go. We hit save, and then we can see. That's curious. We haven't seemed to change it. So this one should be Z. Should be Z. Let's go figure out why that is. Oh, we didn't. We forgot to pass in our mappings. So we updated our mappings, then didn't pass them down, and then it'll keep using the default one. So if we update that, there we go. Now we've got this T0. And just for another example, just because maybe this isn't quite clear, so we've only got one type. Let's say we had a type function application where we have its type function. It's a function type function application, and our news are going to be something like it's going to be a type variable of Z. And then we might have also like another type variable of I don't know. Well, yeah, we'll just say they're both type variables Z. So now we're getting T0 and T0 again, and you see they're the same T0 because we have to know that these are the same, right? When we instantiated, we kind of kept that mapping Z to C0 and both get mapped to T0. If this was say Y, it would stay as Y because it's not for all quantified on Y, so we'd get T0 and Y. If alternatively we did have like another wraparound here where we had like ty, or we can just do that now. It's a type quantifier, and say the body was that, and the name was y. I'm getting a bit confused on the bracketing, but something like that. I'm missing a comma. There we go, and I'll pull that in. Cool. Then we should get T1 and T0. So it's done them in different order. So Y is T0 and Z is T1 because they're just nested that way. But they're all just basically different names. It doesn't actually matter the ordering. And so we got T1 and T0. And we could also have other type function applications like bool or something here, or string, and that doesn't take any arguments. And again, that would just be. Oops. Sorry, we didn't have string. We have bool. We go and update that at some point, but yeah, and then we've got T1 to bool, right? Because we've got this Z there, which is fine. Cool. So that looks like our instantiate function is all working nice and happily. We can go back to our helpers. We can see we've only got two left now, generalize and unify. So let's deal with generalize first. So let's say we want I'll export this, generalize, and it's going to be a function that takes a context, because remember we generalize in a context because we want to check what kind of the free variables are in the context, and so that we are going to for all quantify any free type variables that are not free in the context. So we have some monotype that we're going to generalize into a polytype. First, we're going to find what are the free variables in the type and that aren't in the context. So we're going to find kind of the difference of the free variables in the type minus kind of the free variables in the context. And that's going to tell us what we can use to generalize in this expression. And we need to define all these functions, and we'll get to that in a second. I'll hit that again. And in this case, I'm going to keep wrapping up basically with all these quantifiers. Maybe there's a nicer way to do this with like dot reduce, but I think this is fine. So we'll say we want some polytype t, and initially that's just going to be the type, and then for each of these quantifiers, we're going to wrap that around. So for each quantifier, we're going to say t is going to be type quantifier, and then the kind of symbol, I guess, is going to be that quantifier q, and then the kind of body of that thing is going to be the last one we had, which is going to be t. So what this is going to, and we're going to return that. So what this is building up is basically like the first time it goes around, it will just be the type. So let's say it was like I don't know, basically just whatever it initially started with, and then we're going to add like the type quantifier for like a, and then like wrap that again with type quantifier for b, etc. So it's like going from whatever the type was to adding like a for all a and then a for all b before it, etc. Which is fine. And now we need to deal with these functions. The diff function is like a pretty standard one we can do pretty easily. I guess we need to know the prevars. Those will say we're going to represent as just like an array of strings. So we could say like, A is an array of strings, and B is an array of strings. You could also make this generic pretty easily. Maybe we can do that. We'll do that. We'll make this generic. So we're going to have another generic type variable here. And this is going to say, well, we have an array of t's. We have two arrays of t's, and we're going to return an array of t's that is kind of the first array of t's minus the second array of t's. And this isn't going to be a hugely efficient one, but it probably doesn't matter immensely. And we'll say, take the kind of set of B. So new set of all the elements in B. And then we're going to return A, where we're going to filter out anything that is inside B. So of the values in A, we're going to say B set does not have those values. So that's going to be the values in A that are, B set doesn't have. And the reason we're doing a set is just because it gives us kind of, I think, O of 1 operations on finding out whether it's in the set or not, because it uses some hashing in there. That's why it's unhappy. Cool. So that's our diff function. Next, we can work on our free vars. So let's define a free vars. And this is either going to take a monotype or a context, and should return an array of strings, which are going to be the free variables in that type or context. I'm also going to foresee that we're probably going to call this on the context and all our different types inside of there. And the context, if we remember, was a map from variables to polytypes. So actually I'm going to tweak this to be polytype kind of compatible, so we can call it on any of those. And then returns an array of strings which we can pass into this diff thing later. And what can we do here? Well, again, we can probably, like we did back, where did we do it? Up here, we can do a special case for context where we map everything through, depending on if it's context, and then do different things based on these things. So I'm going to just copy the body of this function. And again, we can make this like a helper function in its own right, where it kind of does this mapping and does this stuff, but I think this is okay. I'm going to give this a name value, just because I don't have to change all this again. Cool. This one is unhappy because we're returning context, but we should really be returning the strings in the context. So we don't actually need to rebuild this context in this case. We just need to go through all the entries in the context and then map them. We don't even need this either, I think, but I think we just need to get the free vars in each of the polytypes. Good, and that gets a string array, which is fine. And then we can just flatten that back down. If we want to make it simpler, I guess we do use object.values just to get the values and ignore the keys completely. And then we can just pass in the value into free vars. And actually, if we're doing this, we may as well just pass in free vars as a function like that. That's kind of neat. So first case, if it is a type variable, the variables inside of it are just whatever the variable is itself. So I guess we can do value.a and just return that. Because remember, any type variable basically creates this new free type variable, and then we kind of can kill off these free type variables with our type quantifiers. So you can go back and watch. I can't remember if we covered it exactly. We definitely covered free variables in the lambda calculus, so free expression variables, and it works basically the same way. So following that kind of logic, we looked at applications and we said, well, in applications, just everything inside of the application. The application function doesn't matter itself. So again, this is probably going to look the same, where we're going to look at the muse. We're going to get each of the, what do we call these, the free variables in the mu. There we go. And again, we got this from, I think actually, we can do the same thing here again. We can do flat map, and I think that might just flatten it as well. Do it all in one. There we go. That's even shorter and nicer. And then lastly, we've got our type quantifiers. Remember, this is where we're going to remove our values. So in this case, it can be the, what we want to do is get the value of the kind of lower one, right? The free vars in that. And we're going to remove basically the one that is this quantifier. So we're going to filter out the value, so the values that aren't this quantifier, which is going to be the value A, I think, which I think should work. gonna hit save. And we can test that out and see if that generalizes correctly. So let's generalize. We can import that. So first we'll need a context. So you can make a context. And initially we want some variables. So let's say we had a variable x, and it is going to have a variable, say t0, right? And then the other thing we're going to pass in is a type here. So we could say if we had a type variable that was t0, for example, this cannot be generalized because we've already got a t0 in the context. And so this t0 seems related to this t0, so we can't generalize at this point. So if I go log that, what we should expect is basically nothing changes and we still just have this t0. We hit save, so we still have t0. If this was called t1, for example, this t1 is now not related to this because it's not the same name. So it is kind of it's free in this thing and not free in the context. And so we should see, yeah, there we go. It's given this a type quantifier, so it's kind of saying, well, now this can be like this isn't just t1. This is actually for all t1, because there are no other restrictions on it that it can apply this for all quantifier because there are no restrictions. Other way, like we could also see, is say like this one was a type quantifier. So let's say this had a nested thing here where it has then a type bar of t0. What this is saying is we have some kind of context. X is of type t0 to, sorry, for all t0, right? And in this case, it's not free because this for all binds it. So this basically, like, you could have another thing called t0. If you had another thing out here called t0, it's like different to this one, basically, because it's almost like scoping, or, you know, it's bound here, so it's not free. And so in this case, it should also be for all here. So if we try this one, we'll see that we also get a type quantifier out where we say, yeah, t0 can be anything it wants to be if we had this. But for example, if this was like t1, for some reason, this is like for all t1, t0, again, this t0 is now like, you know, not free, and so we're going to go back to being like just a type variable, and it's not free. So that's what our generalize function can do. Cool. And lastly, our unification function, which is exciting because I think this is our last kind of helper function that we need. And then writing the algorithm should be really, really simple in terms of just following the paper and implement them. So let's get on with our unify function. Again, we've seen this in the slides. I think we actually looked at them earlier in this video, but this is slightly more complex, so I might get a bit stuck. We'll see how far we get. So let's have a unify function. And remember, what this unification function does is it takes two things. In this case, we're going to take two types. So we can say type 1, it's going to be a type, and type 2 is going to be a type as well. And it returns a substitution, which is going to be a mapping so that when you apply the substitution on type 1 or type 2, it's going to result in the same type. And in this case, you know, yeah, we're going to just deal with monotypes because in the Hindley-Milner algorithms we're seeing, like algorithm W, algorithm M, we only deal with monotypes. You can work on polytypes, but that gets more fiddly because things might not be exactly equal where, say, you've got for all quantifiers and they're renaming things to different things, but structurally they're the same type. So that's a bit more fiddly. But monotypes, pretty easy to figure out if they should unify. So let's start with kind of the rules we should do. So imagine we have, the simplest case is just two type variables, right? Where we have like a type variable A and another one that's also A. And these are the same, and so we should have no kind of substitution going on. So let's deal with that first. So if type 1 type is a type variable and type 2 type is a type variable, and type 1A is type 2A. So this, if they're all, basically if they're just two type variables that are the same thing, then we don't really need to do any work. We can just return an empty substitution. Otherwise, if type 1 is a type variable, so excluding all the other things, let's say we have type 1 as type variable. So we know this is A, and this could be like whatever it wants to be, right? Or really we can say, well, then the easiest thing we can do here is you can just say, well, A then should map to whatever this thing is, because that's going to like solve our problem. Because if we say A maps to this, well, then like solved, right? Because a variable could be anything. It's going to be these question marks, so we're going to map it to that. So that's exactly what we're going to do. We can say type 1's a should then just be mapped to the type 2, right? Which is going to be our kind of question marks. This looks great. The only problem is, what if there's anything like contains a? So for example, if this anything is a to a, or maybe for less confusing, b to a, when we then get to kind of this one, it's going to keep replacing itself infinitely, because it will get to say, this a and see that, oh, well, it should be unified with b to a, and so this should be b to a. And then, oh, well, this a should be then replaced with b to a, and this should be replaced with b to a, etc. And you've actually got an infinite type going on here. And that's not really what we want. That's is dangerous, because it's going to kind of keep looping in infinitely and cause problems. Like theoretically, you can have infinite types, but most practical programming languages don't allow you to have infinite types. And where they do, they use other clever tricks to figure out what is basically going on here. So what we're going to do is going to do a contains check. So what we want to say is if type type 2 contains type 1. Then we need to throw an error. So we can throw a new error and say infinite type detected. And we need to implement this contains function. So this contains function is going to have type. I guess it's weird that I put them the other way around, but that's fine. It should return a Boolean as to whether type 1 contains type 2. And so what is it going to do? Let's think about this. Well, actually, we kind of know type 1 is always a type variable. I don't know if I want to always assume that. I'm going to always assume that just because it makes our life easier here. So does type 1 contain that? So I think we can do our same kind of case-based thing. So you can see a lot of case-based things, which is why implementing this in a functional programming language which has like pattern matching is quite nice, because you just kind of implement it for each of these different patterns. I mean, all of algorithm W is basically one just giant pattern matching algorithm that looks also very similar to this. So getting used to this format helps, I guess, in that. So if type 1 is a type variable, do that, then that, then that. I guess we actually don't have to worry about this being a type variable, because if it was... Do we deal with that case? No, we only dealt with it when they're not equal to each other. Because you can map, like if this was A and then this was just B, A mapping to B would be fine. So like, I guess it's only if it contains it. So if it's type variable, the only way it can contain it is, let's think. Well, I guess like A kind of contains A in and of itself. So you could say if they're equal, that's fine, because then that would cover us if like we had B to A, and then we did it recursively where we check like, well, this thing, we just check each of these, and that works. And it's safe to do that because the initial thing we checked is if they're all the same, then we're going to like get rid of that case anyways. So we can just say, well, it's included it in it if type 1 A is going to be equal to type 2A. Cool. And then for our type function application, again, very similar. I can rename this to value just to kind of keep these consistent. And so this one is, there's some kind of type in our muse that such that the type there, that type contains type 2. That looks good. And then when it's a quantifier, oh, I guess that can't happen because it's just monotype. There we go. So just two cases. Simple. So that's our contains function. Nice. So basically dealt with all the cases where type 1 is a type variable, because like this now terminates. So we've dealt with that. The other way, now we can basically do the kind of reflection if type 2 is a type variable by just recalling this function. So if type 2's type is a type variable, well, in this case, we can just return the same function unify, but the other way around. So we can do type 2, type 1. And so that case, when we call it here, well, then type 1 is going to be our type variable, so that's also dealt with. And so now the only case we could be in is type 1 and 2 have to both be not type variables, right? Which gives us type function applications, because our monotypes have to be type variables or type function applications. So now they're both type function applications. So I think TypeScript should know this already. So if we like look at these, if we hover over them, it says, yeah, both of them are type function applications. So that's the only case we have to deal with now. And so now let's think about that. So one thing we have to do is, like, let's say we had two expressions now. So these are both type function applications. So let's say we had a to b and then bool to int. What we want here is a unification from like a to bool and b to int. That would be our unification. I guess a and bool is like another example where we have I guess this one's already handled, although by this thing, right, where this one is a type variable and then this one is a type function application. So that's already handled for us. So I guess we do need to go for one where they're both type function applications like this. And so in this case, one way we can see that they do unify is they both use the same type function application. If they use different ones, that's just ununifiable, because if you had like a bool here, there's no way that's going to unify here, because this is fundamentally a function. This is fundamentally not a function. It's a Boolean. And so that's kind of a rule we can add in. So if type 1 C is not equal to type 2 C, in this case, we need to throw an error because something has gone wrong where these two types are ununifiable. So we could say like could not unify types. One was a, let's put this in a template string so we can use it. One was a C. Or we'll just say that and type 2.c. You know what? Actually, maybe we can improve this error message a bit. So I don't know, different type functions or something. That looks good. So next, so we know they're both the same type function. The other thing we want to check is that they have the same number of arguments. I mean, really, the function should probably determine the number of arguments. I'm trying to think of a case where that isn't true. I can't really think of a case, but they should have the same number of arguments at least. Anyway, so if the number of muse, so the length is not equal to type 2 muse length, we can throw a different error. So this one is we could not just unify these types where they had I don't know, different argument lengths. I guess like it would be useful to have like a toString method almost on this, or like a thing like that, which I think we could do. But we'll just keep them there, and I think it will like stringify them somehow. It might not be very good, but we'll see what the error message looks like. Maybe we could like do JSON stringify or something. That's probably fine for now. And so they're the same type, they're the same length, and now what we need to do is, so like let's say we have two functions. We've got we can go back to our example here where we had a to b and bool to int. What we need to check is basically need to unify them kind of pairwise. So a maps with bool and b matches with int. So like these unify and these unify. So we should basically iterate through those two different ones and unify all of them. As we unify, what we'll get is, say, the first one we have a is bool, and so we'll end up with like a substitution. A should be mapped to bool. And then the second one will get b to int. What we need to do is we actually need to apply the substitution first and like basically collect these constraints as we go along. Because otherwise, if we had something like a to a, it maps with bool to int. What we'd end up with is like a to bool and then a to int if we did it separately. And then these two, like combining them, there's like, if we tried to combine them, we'd lose some information or something would go wrong anyways. And like fundamentally, this type doesn't actually unify because this requires this like something going to something that is the same thing, and this is different. And so, if we use this constraint first and then we checked, okay, well, this should be now a bool, and then try to map these, then we'd know they're different type constructors. So we throw this thing. So like we've got to check there in that case, basically, that we're unifying along as we go, and also we're collecting those constraints as we go. So we're combining them. So let's give that a go. So in this case, let's say like our combined substitution is going to be some kind of substitution. Initially, we'll just make a new substitution, which is just empty. And then as we go along, so we'll go through the thing. So we know they're the same length, right? So it doesn't really matter which one we iterate through. And here we're going to unify these two. So we're going to unify type 1 muse I with type 2 muse I. And then what we're going to do is we're going to take this substitution that we've just got from kind of unifying these two, and we're going to update our combined substitution with that. So our combined substitution is going to be kind of, I guess, combining these two. And remember, we had like the little function where if we could take a substitution, then that would combine them. So that's going to unify these and then combine it with our combined substitution. And then also, before we actually unify these, we need to apply the substitution to them to actually apply that kind of throughout. So we're going to call it that. Just because combined is a bit confusing, I'm going to call this like S or something for our substitution that we're going along here. That should hopefully like make it a bit clearer what's happening here. Is we're applying the substitution to both of them, and then we're running unify on them, and then we are combining that with the other substitution, and then using that as our substitution, and kind of iteratively doing that. So as we go along, we collect these constraints in like one big substitution, this S, and then we can return this substitution S, which is going to be our unifying substitution, which has unified all the constraints through the different variables. Cool. So that's our unification algorithm done. That's looking pretty good. I think that's all our help has done. And so next we should be able to, I mean, we can test this unify function. So if I want to do unify this, so we'll do that and log our substitution. And let's say we have two types. So we have, what was the example? Got rid of the example now, but we had, I think, a type function application where we had a function type function. And then the muse we had were on this one, it was A to B, I think. So we had a type of type variable A and B, and then that all should unify with, let's say we have a type function, and this one is, I think we had like int to bool or something. I can't remember which way around it was, but it looks something like that. Anyways, let's just get the types working on here. Something like that. And so now when we check this, so unifying these two, what we end up with is the substitution, and we look at what the substitution like raw bits are. Well, it's mapping A to int and B to bool, which is kind of exactly what we expect. And similarly, if we change this round, so we move this one here and this one here, what we're going to get is like basically the same thing. So it's still matching across them. So this is like trying to unify A to bool and int to B. That's basically what we've written here, right? A to bool and int to B. Well, then it's still going to map A to an int and B to a bool, right? Because that's what kind of these unify as. And if we did something that didn't unify, so for example, we did, let's say we had that example, A to A and int to bool. These two aren't going to unify because like A can't be both int and bool. It's just like these are different, whereas these ones are the same. So if we had A to A and int to bool, what we should see is we should see an error. There we go. So if thrown an error, could not unify types, different type functions, int and bool. There we go. So our unification function looks like it's working as expected, and that's all good. So I think that's about it for this video. We've looked at creating our models for everything. So we've got our expressions, right, where we've got variable, application, abstraction, let expressions that are all represented here. We've got our types, monotypes, polytypes, type functions, all our variables, applications, quantifiers for types. And then we've also got our context. And then we've also got a bunch of helpers, right, for our substitutions. We did all that work on our substitutions. We've got helpers for creating new type variables, instantiating things, generalizing things, as well as unifying types. And all that together are all the helper functions we need for implementing algorithm W and algorithm M to run Hindley-Milner type inference. Oh, we also did the parser for, we can pass in a string and now it should generate a expression. So we'll see, we should be able to kind of give it a string expression and it should be able to infer the Hindley-Milner type or give us an error once we've implemented our algorithm W and algorithm M in the next videos. So thanks for watching and see you then.